Solutions and concentration are going to be the topic of this first lesson in a whole chapter on solutions. In the second lesson, we'll go through dilutions and what's called solution stoichiometry, kind of stoichiometry applied to solutions. And in the last lesson, we'll talk about what are known as colligative properties. Now, this lesson's part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so if we're going to have a discussion about solutions, we've got to get some vocabulary out of the way first. And so it turns out a solution always implies you have a mixture. And again, if you're probably at least already familiar with in principle what a solution is, or at least examples of it. You might think of like salt water or a can of soda. But a solution always implies a mixture of at least two substances. So if you've got salt water, you've got salt and you've got water. And we put those two substances into one of two categories, either the solute or the solvent. And the solvent is usually the major component, and all the examples we're likely to encounter in this chapter, the solvent is going to be a liquid, and quite often it'll end up being water, in which case we call it an aqueous solution. We encountered those back in chapter 4. The solute, on the other hand, might be a solid, a liquid, or a gas, and we'll encounter all three. Now, in principle, solvents actually can be solids or gases in addition to liquids. It's just not going to be any of the examples we're likely to encounter in this chapter, in this course. All right, so if you think of like salt or sugar dissolved in water, your solute is a solid, and then water is your liquid. So if you think of ethanol dissolved in water, and ethanol is kind of the alcohol component in like drinking alcohol. So if you think of like a typical beer, about 5% ethanol, well, what's the other 95%? Well, most of that other 95% is water. If you think about wine, it's about 12% ethanol, and most of that other 88% again turns out to be water. So you've got a liquid solute, the ethanol, dissolved in a liquid solvent, the water. All right, so if you think about a gaseous solute, so you could think of like O2 in water. So what do fish breathe? Well, fish breathe oxygen, O2, just like you and I do, except they're not getting it and pulling it out of the air. They're pulling some O2 that's actually dissolved in the water. So this is why if you take a fish in a fishbowl, if you cover up that fishbowl and leave it covered for a long period of time, so that fish is going to die. It's going to run out of O2. It'll use up all the O2 that's in the water. As a fish, pulls the O2 out of the water, more actually dissolves from the air in it. But if you cover it off and close that off, so no more O2 can get into that water. And so once the fish exhausts its supply, it's out and it perishes. So cool, there's some examples again of both solid, liquid, and gaseous solutes in a liquid solvent. Now, we often talk about what's referred to as solubility, and solubility refers to how much of a particular solute you put or dissolve into a particular solvent. So we encountered this also back in chapter 4 when we looked at the solubility of different ionic compounds in water. And we actually really just went to two extremes. We put soluble as a label or insoluble. And we had a list of rules that we could look at to figure out if an ionic compound was going to be soluble or insoluble. Well, the truth is it's a whole spectrum. You've got a whole range of solubilities that are possible. And oftentimes we'll put these in so many grams per 100 milliliters or something like this. But the truth, again, is that there's a whole range of solubilities possible. But for convenience sake, with ionic compounds in water, we just said, let's kind of draw a line in the sand. And that line's either like 0.01 molar or 0.1 molar, depending on who you talk to. And if it's more soluble than that, we'll call it soluble. And if it's less soluble than that, we'll call it insoluble. But the truth is there's varying degrees of solubility from ionic compound to ionic compound in water, and for other substances in any solvent you want to choose. So that's solubility. And so along with solubility, we've got three related terms: saturated, unsaturated, supersaturated. And we say that a solution is saturated when the maximum amount of a solute is dissolved in that solvent. And again, this varies. For things that are not very soluble, it's going to be a low amount of solute in the solvent to reach that saturation point. But if you got something with a rather high solubility, like say NaCl, table salt, in water, then you can pour a ton of table salt in water till you reach that saturation point. Now, you've reached that saturation point when if you go past that point and pour just a little bit more in, it doesn't all dissolve. Even when you stir it, it doesn't all dissolve, and you'll see some settling on the bottom. And it takes a lot of salt to get there because salt has a high solubility. But if you use something like silver chloride, AgCl, instead, you could actually put a pinch in water, And in all likelihood, if it's just a glass of water, not all of it's going to dissolve, and some of it's going to sink to the bottom because AgCl has a very low solubility. So, but again, saturated just refers to reaching that maximum point where the most amount that could be dissolved is dissolved. And again, that's different for different solutes and different solvents. Now, unsaturated is when you're below that point. You're less than the maximum in there. So if you pour a pinch of NaCl, salt, in water, so in a glass of water, like let's say, you're going to be below that saturation point. And again, you put another pinch in, and you're probably still below that. And as long as you haven't reached that maximum to where some of it just settles onto the bottom, even when you stir it, so you're in an unsaturated solution. So, and then we have something called a supersaturated solution, which is an unstable and rather rare event. And supersaturated is a temporary unstable situation where you actually have more than the normal maximum amount dissolved in a liquid, in a solvent. So, and again, this is not a normal situation. So, and it's not something that's often easy to achieve, but it is something we can replicate. And so a good example of this is if you've ever made rock candy, and some of you have and some of you haven't. It used to be a much more common activity when I was a kid. So, but rock candy is made when you heat up water. So it turns out that the solubility of a lot of ionic compounds, or a lot of solids, I really should say, in general, including sugar, which is not ionic, but including sugar, those solubilities increase at higher temperatures. And so if you heat water up to near boiling, you can dissolve a whole lot more sugar in it than if you try to do it at room temperature. And so that's what we do with rock candy. We heat up water and dissolve a ton of sugar into it, and we make a saturated solution. We dissolve the maximum amount of sugar possible. So, and it turns out though that if you slowly cool that water down slowly, and you don't agitate, the container it's in and stuff like that, so that as you cool it down, the solubility of the sugar goes back down again. And so as you approach room temperature, what you're going to find is that the sugar actually stays dissolved. And you end up with what's called a supersaturated solution, where temporarily, in an unstable situation, you have more than the normal maximum. We had to get creative on how we create this. If you just tried to do it at room temperature from the get-go, it actually wouldn't work. So it turns out if you take that supersaturated solution of sugar water and you put something with any kind of irregular surface on it, whether it be a piece of string or say a popsicle stick, or just drop an actual sugar, a solid sugar crystal in there, all of a sudden you'll just get sugar crystals forming everywhere. And as evidence of that unstable situation, that abnormal situation where you have more than the normal maximum dissolved, and that's supersaturated. So I just want you to realize again that this is not a usual thing. It's an abnormal thing. All right, so this is our vocabulary. I just wanted to get you familiar with, and some of the, there's some other vocab out there and stuff like that we could have talked about. We could have talked about like miscible and immiscible and things of a sort, but I'm going to eliminate those. You're going to see those in college. You're not likely to need those in your high school course. So let's move on to talking about concentration. All right, so in chemistry, we've got several different ways we can express concentration. You can talk about the concentration of the solute in the solvent, but you can actually also talk about the concentration of the solvent as well. But much of the time we'll be actually referring to the concentration of specifically the solute. The one exception we might see is talking about mole fraction in one special case at the end of this chapter when we're talking about these colligative properties. But most of the time when we're referring to concentration, we're referring to the concentration of the solute in the solvent. And so the most common way you're going to encounter in chemistry is what's called molarity. So, and molarity is symbolized by a big capital M. So, and it's equal to the number of moles of solute over the number or the volume in liters of the solution. And it's important that this is of the entire solution, the solute and solvent combined. So, because we're going to see molality in a little bit, that is actually related to the number of moles of solute relative to the amount of just solvent alone. So, but molarity deals with the entire volume of the solution. It counts for the volume of the solvent, but again, when you add solute, it actually is going to cause that whole solution volume to rise, and molarity accounts for all of it. So N here stands for the moles, in this case of the solute, over the volume in liters of the entire solution. Now, molality you'll use a little less commonly, but we're definitely going to use it towards the end of this chapter for a couple of those colligative properties we'll study. So in this case, it's moles of solute over the kilograms of solvent. And so it kind of gives us a ratio of solute to solvent ratio instead of solute to the entire solution ratio. So we'll see some similarities when we're talking about aqueous solutions between these. We'll find out with aqueous solutions, these numbers are often pretty close. So only because 1 liter of water happens to weigh 1 kilogram. And if you have a dilute solution, well, then it's mostly a dilute aqueous solution anyways, it's mostly water. And the volume of the solution will probably be pretty close to the volume of just the water. So So for dilute solutions in water, these are often very similar numbers. So, but if you're not using water, or as you get more and more concentrated solutes, so these numbers start to diverge more and more. All right, then we have what's called the mole fraction, and mole fraction is exactly what it sounds like. It is the fraction of the moles that are either the solute or the fraction of the moles that are solvent. So if I have like 1 mole of solute and 9 moles of solvent, well, the mole fraction for the solute would be 1 out of 10, or 0.1. The mole fraction for the solvent would be 9 out of 10, or 0.9. So that's all a mole fraction is. It's kind of like taking a percentage, except you don't multiply by 100 at the end. And then mass percent is exactly what it sounds like. It is the percent of the mass. And again, we're usually referring to mass percent for the solute. So it is just the percent of the total mass of the solution. So that is the solvent. And so in this case, I mean, that was the solute, I should say. And so in this case, it's the mass of the solute all over the mass of the solute plus the mass of the solvent times 100, just like you'd find the percent of anything else. Now, technically, we often, in addition to mass percent, sometimes we use like what's called a parts per million or a parts per billion for things that are rather dilute. Now, technically, a percent, cent means 100, so percent or hundredth, depending on how you look at it. And so a percent is a part per 100. So a part per 100. So a part per million has the same general formula, except instead of multiplying by 100 at the end, you multiply by a million at the end. A part per billion has the same general formula, but again, you multiply by a billion, or 10 to the 9th at the end. So, and again, for rather dilute things, like sometimes we'll talk about, the concentration of some pollution gas in the air. So oftentimes those get convenient to talk about them in parts per million or parts per billion because they're present in much lower concentrations, or maybe it's the concentration of lead in a lake. So, and again, lead being toxic, it's got to be below a certain level, or, humans shouldn't be swimming in that lake, kind of a thing. But again, we're usually talking about it on the order of like parts per million or parts per billion, rather low concentrations in such cases. So that's where those might enter in. And so it turns out we got all these different ways of measuring concentration. So, and you might use all of them. Again, you'll use molarity more often than all the rest. So, however, we're going to use an example, and we're going to kind of express a concentration in one set of units. We'll use a mass percent, it turns out, to start with, and then we'll just kind of convert it into the rest of them here. So the one example we're going to use here is we're going to have a 20% solution of H2SO4 in water. So that's the solution we're going to have. So that's the mass percent. It's 20% mass H2SO4, which means obviously then it's 80% water is the rest. So H2SO4 is the solute, water is the solvent. And the question is then, what is the molarity of that solution? What is the molality of that solution? And what is the mole fraction of H2SO4 in that solution? And we're going to go solve those. All right, so it turns out all these, measures of concentration are what we call intensive properties. We talked about those intensive properties way back in the first chapter when we talked about matter. And an intensive property means it is independent of the size of your sample. I don't care if you have a big sample or a small sample, it is a property that's fixed, and concentration is one of those types of intensive properties. So it doesn't matter what size sample of this 20% H2SO4 we have, so the mass percents would be the same regardless of sample size. And so in this case, it's going to be rather convenient for us maybe to consider that we have a 100-gram sample, just to make the math easy. Because I can do 20% of 100 and 80% of 100 really easy. And so in this case, I don't even have to pull out my calculator just yet and see that, well, 20% of 100 grams is 20 grams. And so we've got 20 grams of H2SO4. And again, the remaining 80% is water, and 80% of 100 grams is 80 grams. And so we've got 80 grams of water. And so now we want to turn this into a molarity, a molality, and a mole fraction. So, and the molarity is actually going to be the toughest of these, and we'll do that last. So let's start with molality in this case. So with molality, we need moles of solute, and again, the solute is H2SO4, so we got to convert this into moles, and then we need kilograms of solvent, so we have to take our 80 grams of water, the solvent, and turn that into kilograms. And so we can do some simple conversions here. So with that 20 grams of H2SO4, well, I want to convert that into moles in this case. So I'll need the molar mass, and 1 mole of H2SO4 turns out, if you add up, there's 2 H's, that's 2, sulfur is 32, 4 oxygens are 16 each. 4 times 16 is 64, plus 32 is 96, plus 2 is 98 grams per mole. And so our grams will cancel. We'll end up with an answer. Oh, the per mole is actually already implied grams per mole, so I shouldn't write it there. So, but we'll get an answer in moles of H2SO4 here. So in this, we'll need our calculator for. So we'll divide 20 by 98. And we're going to get 0.204. I'll leave my rounding till the end. So 0.204 moles of H2SO4. And then once again, we're going to turn our 80 grams of water into kilograms of water. And in that case, we'll just divide by 1,000. So, because we've got 1 kilogram is 1,000 grams of anything. And so we're dividing by 1,000, and we're going to get 0.080 kilograms. So if we come back over here to our calculation for molality then we're going to take our 0.204 moles, divide that by our 0.080 kilograms. So, and I've got 0.204 here, but I'm just letting the previous calculation with all sorts of decimal places ride all the way to the end here. So I'm going to divide this by 0.08 and get 2.55. So, and the little m here stands for molality. Lowercase m is our abbreviation there. So it's a 2.5 molal solution, we would say. Okay, so next thing we can do is find the mole fraction. So, and our mole fraction, again, is just the fraction of the moles that are our solute in this case. And so in this case, again, this is going to have a formula, moles of H2SO4 over the total number of moles, which incorporates the H2SO4 and the water. And so we already know the moles of H2SO4 here is, again, that 0.204. But we're going to divide that by the moles of H2SO4 plus, and now we need the moles of water. And so instead of turning our 80 grams into kilograms, now we're going to convert that 80 grams into moles. And so in this case, 80 grams of water, and again, connection between grams and moles is our molar mass right off the periodic table, and oxygen is 16, each of the hydrogens is 1, so it's about 18 grams per mole. So 1 mole of water is 18 grams, and so 80 divided by 18, we'll pull out our calculator yet again, gets us 4.44, and it's actually 44444. All right, so in that case then, 0.204 divided by the total number of moles, which is the 0.204 for sulfuric acid, but the 4.44 moles of water. That'll get us our mole fraction here. So in this case, we'll again take that 0.204, and once again, I'm using the entire saved number there, and we'll divide that by the total of the 0.204 plus the 4.44, which I can, again, pull the entire number. All right, 0.0439 is our mole fraction. All right, so we've got one calculation left, and like I said, this is going to be the most challenging one, and that is our molarity. So, and the molarity is so challenging is because we've got to figure out the volume, and to figure this out, so we actually had to provide a density calculation here as well, or a density number. And it turns out the density of this lovely 20% solution is provided as 1.16 grams per milliliter. Let me make sure that's right here real quick. And that density is provided as 1.14 grams per milliliter. All right, so this is going to be a little more challenging here. So, because now we need moles of solute, but now we need it over the total volume of the solution. So, and you might recall that density here is mass over volume. So density is how we relate mass to volume. And so in this case, we've got 100 grams of our solution, and we need to convert that into the total volume in liters of the solution. So that's what our density is going to allow us to do. It's going to allow us to turn the grams into the milliliters. If we rearrange this here, we can say that volume equals mass over density. One way to look at it, or we could actually just kind of do the dimensional analysis and do a conversion here. So we're going to take that 100 grams yet again. And in this case, we'll multiply by 1 milliliter over 1.14 grams, and you can see the grams cancel. Notice this is ultimately the same thing as taking the mass divided by the density. The mass divided by the density to get the volume in milliliters. So, but then we want to take and convert that milliliters to liters, and 1 liter is 1,000 or 10 to the third milliliters. And that'll get us our total liters here. So 100 divided by 1.14 and divided by 1,000. It's going to get us 0.0877 liters. Okay, so once again, our molarity is moles of solute over the liters of solution. And now we can see that that liters is 0.0877. And in this case, we already figured out the moles of solute. We took our 20 grams of H2SO4 and used the molar mass to figure out that that was 0.204 moles. We'll use that number once again. And if we do that calculation here, so 0.204 divided by our 0.0877, we're going to get 2.33 molar solution. Let's write it there. 2.33 molar with a capital M this time. And if you recall, we said that molarity and molality for rather dilute solutions in water often appear to be fairly close to the same number. So 2.33 versus 2.55. And this is actually a rather concentrated solution of solute, it turns out. So as you got more and more dilute, though, these numbers would get closer and closer together. But even so, with a rather concentrated solution, they're not that far apart. So, and this is how we kind of use all the different units of concentration and how we convert amongst them. Now, if you have found this lesson helpful, would you do me a favor and give me a like and a share? A couple of the more helpful things you can do to make sure other students see this lesson. If you are looking for the study guide that goes with this lesson, if you're looking for practice materials, check out my premium course on chadsprep.com.